All right, thanks for tuning in to another episode of Check This Out Mathematics. And I encourage you to like these videos and subscribe to the channel and make some comments and watch more videos so I can continue to bring more content. Now, in this series of videos, we are looking at formulas that generate Pythagorean triples and the underlying concepts. And so these are the three formulas that generate Pythagorean triples that we have talked about in previous episodes in this series. And this first one we covered a few videos back. And this one we just covered. And so now we're going to look at this third formula that generates Pythagorean triples. And want to make a connection first. Here in this second formula that generates Pythagorean triples, and in the first one. In the first one here, we excuse me, we needed a single value of m, and then here in the second one we needed two values, m and n. And the thing about this one is when we had two values for m and n, this formula that generates Pythagorean triples had a subtraction in it. And so we had to put a restriction on m and n, saying that m had to be greater than n, so that this expression would always come out to be positive. But now, in this third formula that generates Pythagorean triples, you'll notice that we have a basis of two values, an s value and a t value, and notice that they're all pluses. And so in this arrangement here, there's no restrictions on s and t. So that's how this one is different there. And so let's say that here. This is the Pythagorean triple generating formula that we're going to discuss in these next couple videos. And so when you have two values, s and t, pair values, where s and t are elements of the natural numbers, the counting numbers, 1, 2, and 3, that if you plug in an s value and a t value into these algebraic expressions, you'll always get an a, b, and c, where a squared plus b squared equals c squared. And let's clarify that s is can be greater than t, t can be greater than s, and s can actually be equal to t. So there's no restrictions on s and t. They can be, since everything is addition here. And so s could be greater than t, or t could be greater than s, or they could even be equal. And when they're equal, they give you a Pythagorean triple. So let's look at some of those Pythagorean triples that are generated from this formula. And so let's say that we have s and t equal to 1, 1. So here the s and t values are equal. And so now we're going to run it through this these series of algebraic expressions. And so the first one is 2st plus 2s squared. So that's 2st plus 2s squared. And that means we'll have 2 times 1 times 1 plus 2 times 1 squared. And that will give us 2 plus 2, and that gives us 4 there. Okay. And so now then, let's run it through the next expression. 2st plus t squared. Okay. So let's just clarify this here. I've been thinking about Pythagorean triples in numerical order, where the a value is the smallest and the b value is the next value, and the c value, of course, is the highest value. And sometimes this expression will generate the a value in that fashion, and sometimes it will generate the b value in that fashion. And so these two expressions here could be either the a or the b value if a and b and c are in a numerical order. But of course, this last expression is always going to be c here. Okay, so let's continue to plug in 1 and 1 for s and t here. And so we have 2 times 1 times 1 plus 1 squared, and that's giving us 2 plus 1, that's giving us 3. Okay, and now as you can expect here, when we do the 2st plus 2s squared plus t squared, that we're going to get 2 times 1 times 1 plus 2 times 1 squared plus 1 squared. And so that gives us 2 plus 2 plus 1, and that gives us 5. Okay. So you can see from this this expansion here that when we plug in 1 for s and 1 for t, we're getting the 3, 4, 5 Pythagorean triple here. So let's say that here. This gives us the 3, 4, 5. Okay, so that's something interesting about this particular formula that generates Pythagorean triples, that s and t can be the same values. And that's how we get the first Pythagorean triple, 3, 4, 5. Okay, now then, let's show that we can switch the values. So let's pick 1 and 3 as our s and our t. Okay, so we have 2st plus 2s squared, and that's going to be 2 times 1 times 3 plus 2 times 1 squared. Okay, so we're substituting in 1 and 3 for s and t here. So you've got the 1 times 3 and then the 1 squared there. And so then that gives us 6 plus 2. That's giving us 8 there. Okay, so now let's do the next portion. That's 2st st plus t squared. And so now then we have 2 times 1 times 3 plus 3 squared. Yes. Okay, so s and t are 1 and 3 there, and so we have 1 times 3 times 2 there, and then the t value, 3 squared. And so now then we have 6 plus 9, that's 15. Okay, so the 3 squaring is giving us 9, and this is 6 here, and that gives us 15. So we have 8, 15, and you're expecting the next one to be 17. So let's show that that happens. So we have 2st plus 2s squared plus t squared. And so you know, you can look at this even quickly here. You know that this part of this is going to be 8, and this is going to be 9, and that's going to give us 17. Okay, but let's go ahead and go through the motions there. So we have 2 times 1 times 3 plus 2 times 1 squared plus 2, not plus 2, plus 3 squared. So we're plugging in the 1 and the 3 into the algebraic expression here. And so then you will see that we have 6 plus 2 plus 9, and that's 8 and 9, that's 17. Okay, so 1 comma 3 for s and t gives us another primitive Pythagorean triple. That's the 8, 15, 17. Okay, so let's establish that on our slide there, that this s and t values give us the 8, 15, 17 Pythagorean triple. Okay, all right, and so now let's switch the numbers. So 3 and then 1. Okay, so now we're going to say 3 comma 1 as s and t. Okay, and so now we're going to plug that into our arrangement. 2st plus 2s squared. That's going to give us 2 times 3 times 1 plus 2 times 3 squared. Okay, so s is 3 this time here, and so we have 3 squared there. And so now then that's going to give us, that's 6. And here, remember that we need to do our exponent first. So 3 squared is 9 times 2 is 18. So that's 18 equals, that's 24. Excuse me there. So again, 3 squared is 9 times 2 is 18, and 6 plus 18 is 24. Okay. So now then, let's do the second algebraic expression here. This is 2st plus t squared, and that's 2 times 3 times 1 plus the t value is 1 now. Okay. And so 1 squared for the t value here. And so then here we get 6 plus 1 equals 7. Okay, and so now let's go ahead and do the c value. That's 2st plus 2s squared plus t squared. Okay, that third expression gives us the c value. And so now plugging in 3 and 1, we have 2 times 3 times 1 plus 2 times 3 squared plus 1 squared. Okay, and so the 2 times 3 times 1 is 6, as we said before. And the 2 times 3 squared is 18. And then, so we have 6 plus 18 plus 1. And 6 plus 18 was 24, so this is 25. Okay, and so now this 3-1 combination generates the 7, 24, 25 Pythagorean triple. And so let's write that down here. Okay, so that's kind of nice here. The 3-1 combination gave us a primitive Pythagorean triple, 7, 24, 25, which you can see right here. And then the 1-3 combination gave us 8, 15, 17, another primitive Pythagorean triple. And that's this one right here. Okay, so that's pretty cool. We can have the s and t values the same, 1 and 1, and we can have the s value greater than the t value. 3 is greater than 1, and get a Pythagorean, primitive Pythagorean triple here. And then we can switch them where the here the s value was greater than the t value, and here the s value is smaller than the t value. And so, and that gave us another primitive Pythagorean triple. So we can have them be equal. We can switch the s and t values. And so that establishes these 3 ideas here. Okay, and so now let's just look at a few more ideas here that I have from my list. Let's do this one. Okay, so we're going to say 4 and 3 as s and t. Okay, so let's plug that in. We have 2st, so that's 2st plus 2s squared. And so that's 2 times 4 times 3 plus 2 times 4 squared. So plugging in 4 and 3 for s and t. Then we have 2 times 4 is 8 times 3 is 24. And then this gives us, so that's 24. 12 times 2 is 24. You can look at it that way. And then here's a 16. 4 squared is 16 times 2. That's 32. So we have 24 plus 32. And that's going to give us 56. Yes. Okay. And then let's do the next part of the algebraic expression, 2st plus t squared. So that'll be 2 times 4 times 3 plus 3 squared. And again, 2 times 4 times 3 is 24, and 3 squared, that's 9. So 24 plus 9, that's 33. Okay, and then if we do the C part of the algebraic expression, we have 2st plus 2s squared, 2st, no, that's 2s squared, plus t squared, and so then that's plugging in s and t. We have the 2 times 4 times 3 as before, and then we have the 2 times 4 squared, that's the s value, yep. And then the t, that's 3 squared, and so then that's this again is 24, and the 2 times 4 squared, that's 32, and the 3 squared, that's 9 again. So we have 24 plus 32 plus 9. And so when we did that here, that gave us 56. And plus 9, that's going to give us 65. And so this is a pretty cool Pythagorean triple here. And we're not going to write it in numerical order this time. We're going to write it just as it happened here. 56, 33, 65. Because Mr. O'Donnell happens to like palindromes. We'll do a video on palindromes later on. And here's a palindromic Pythagorean triple, 56, 33, 65, and reading it the other direction, 56, 33, 65. Okay. So it reads forwards and backwards the same way. Pretty cool. Okay. All right. Now then, let's look at one more thing that's pretty cool about this type of Pythagorean formulas that generate Pythagorean triples. And so let's notice something, that when we did well, let's see. Yeah, so we did 1, 1, and that gave us the 3, 4, 5. Right? That's that S and T value gave us the A, B, and C value there. And now, if we happen to do 2, 2, and 3, 3, the 2, 2 value let's actually go through that and the 3, 3 value. Let's do the 2, 2 value. So if we have 2, 2 as S and T, and so then that's 2, everything's going to be 2s. So, okay, so 2ST plus 2S squared. That's 2 times 2 times 2 plus 2 times 2 squared. And that's 8 plus 8, that's 16. Okay. And then if we have the 2st plus t squared, that's going to give us 2 times 2 times 2 plus 2 squared. Okay, and so here again we have 2 times 2 is 4, times 2 is 8, and then 2 squared is 4. So we have 8 plus 4 is 12. And then we have 2st plus 2s squared plus t squared. And so that's 2 times 2 times 2 plus 2 times 2 squared plus 2 squared. Okay, so we've plugged in 2's everywhere. And then once again, this gives us 8, and this gives us 8, and this gives us 4, and so we have 20. Okay, so this gives us the 12, 16, 20 Pythagorean triple. If we go back to writing them in numerical order. Okay, so 2, 2 gave us 12, 16, 20. And that's just a multiple of the 3, 4, 5. That's 3, that's the 3, 4, 5 times 4. Okay, so when we had 2, 2, that gave us the 12, 16, 20 Pythagorean triple. And that's just 3 times 4 and 4 times 4 and 5 times 4. So that's just this is a multiple of this original or primitive Pythagorean triple. Okay, and so now if we did 3, 3, and I'll leave that up to you to do, that gives us 27, 36, and 45. Okay, so if we take 3 and 3 and run it through this, our generating formula here, then we will get the 27, 36, 45 triangle. And that's, again, a multiple of the 3, 4, 5. And that's times 9. Okay. So 3 times 9 is 27, and 4 times 9 is 36, and 5 times 9 is 45. And so it appears that whenever the S and T values are the same, so when S equals T, then we're getting a multiple of the 3, 4, 5 triangle. And so let's see why that's true, just for fun, right? That's why we do math, for fun, right? Okay, so here's our formula. 2st plus 2s squared, and then 2st plus t squared, and then 2st plus 2s squared plus t squared. Okay, that's our formula that generates Pythagorean triples here. And so now, if s is equal to t, then we want to show the idea that we get always get a multiple of the 3, 4, 5 triangle in here. So I have k as our multiplying value. So this is the 3, 4, 5 triangle, but it's some a multiple of that, some 3 times k and 4 times k and 5 times k. And so let's just, since s is equal to t, let's just put t everywhere. And so we have 2 t plus 2t squared plus, okay, so that's the first part of our Pythagorean triple generating formula here. And so we just put t everywhere. TNT, dynamite. Okay, so then we have, that's 2t squared plus 2t squared. And that's 4t squared. Okay, so when we put t everywhere in this expression, we get 4t squared. And so now let's put t everywhere in this expression. So we have 2s, no, we're putting t in place of s, right? t plus t squared. And so now this is 2t squared plus t squared. So that's 2t squared plus t squared. And we get 3t squared. Okay, you see how this is working out pretty cool, right? All right. Okay, and so now then, if we have 2tt plus 2t squared plus t squared. Okay, so that's putting t and t here instead of s, because in this case s and t are equal. And so then we get 2t squared plus 2t squared plus t squared. And so we've got 2t squared, another 2t squared, and one more t squared, and so that's 5t squared. Alrighty then. Okay, so nice little idea that whenever s and t are equal to each other, we'll always get a multiple of the Pythagorean triple 3, 4, 5. And so that's what we were talking about right here. So, neat fact. Okay, neat proof. All right, Now in the next video, we are going to take this, we're going to show how this Pythagorean triple generating formula came about. And then I think we'll have to do one more video where we actually run this through the A, B, and C to show that in fact it works as a solution to the Pythagorean triple. Okay. All right. Thank you for tuning in to check this out, mathematics. And be sure to like these videos and subscribe to the channel and leave some comments and watch more videos. As soon as we get off this Pythagorean triple idea, we'll be going into some more interesting ideas that you'll probably like. Okay, thank you, Mr. O'Donnell, signing off.